Hello, my name is Vukašin Stojisavljević. I'm one of the co-authors of the paper entitled Persistent Transcendental Bézout Theorems, published in Forum of Mathematics Sigma. This is a joint work with Lev Buhovsky, Iosif Polterovich, Leonid Polterovich, and Egor Shelukhin. I will now give a short presentation of our work. The starting point is a realization that a number of interesting objects which appear in nature exhibit oscillatory behavior. So here is an example of spherical harmonics which appear in the model of the hydrogen atom. On the picture, you may see spherical harmonics represented by different colors. Red regions represent parts of the sphere where the function is positive, while blue regions represent the part of the sphere where the function is negative. On the other hand, the polar radius in the picture represents the absolute value of the spherical harmonic. You may see that when the function changes from red to blue, the sign is changing. On the other hand, the size of these regions also dictates the amplitude of oscillations. As we can see in this picture, spherical harmonics oscillate quite frequently and the amplitude is changing. This leads us to a natural question, which is how to process highly oscillating functions. The answer which we wish to give is motivated by topological data analysis, and the motto is to ignore small oscillations. In our work, we apply this philosophy to a problem in complex analysis, and we see that ideas and methods which originally were coming from applied mathematics enter pure mathematics and influence it significantly. I will now start explaining our results by first recalling the classical problem in complex analysis which we are trying to solve. First, let me recall a Bézout theorem. This is a classical theorem which says that the number of zeros of polynomials is generically equal to the product of degrees of these polynomials. Now, we would like to have a similar statement for more general functions, for example, for entire functions. And this problem is called transcendental Bézout problem. It asks if we can count zeros of entire maps from Cn to Cn, and can we find some relation to the degree of such maps. Here, entire maps are understood as holomorphic maps everywhere on Cn. So the starting philosophical point of this problem is Serre's famous Gaga program, which, roughly speaking, wishes to relate projective analytic geometry to algebraic geometry. A sample result from this program is Chow's theorem, which states that if we have a complex submanifold of Cpn, closed one, then it is necessarily algebraic. Our idea would be to try to have something similar in the affine situation. In other words, if we would replace Cpn by Cn. However, one realizes that naive attempts to generalize fail, as can be seen from very simple examples. So for example, here is a function mapping C to C, given by f of z equals e to the z minus 1. Now we see that the zero set of such a function is equal to the following sequence of points, and such a sequence of points is actually not equivalent to any algebraic proper subset of C. The reason being that it is unbounded and in fact not finite. So now an idea is to find some notion, some quantity which replaces the degree of a polynomial, and it applies to entire functions. To this end, let us denote by B of r the closed ball of radius r, and we introduce the maximum modulus function as mu of fr equal to the maximum over the ball of radius r of the modulus of f of z. This maximum modulus function in a way behaves like a degree. So here are some degree-like features. For example, if we look at the ratio of the log of the mu and log of r and see how it behaves asymptotically, we may see that if lim sup as r tends to infinity of this ratio is less than k plus 1, then f is in fact a polynomial of degree at most k. This statement is a generalization of the classical Liouville theorem. And indeed, if you would assume that mu is bounded, then we would see that the lim sup on the left-hand side is equal to 0. And by plugging in k equal to 0, we see that f is a polynomial of degree 0. In other words, f is a constant. Another degree-like feature exhibited by maximum modulus function can be seen by using Jensen's formula. So let us denote by zeta f of r the number of zeros of f inside of a ball of radius r. Moreover, we also assume that f of 0 is not equal to 0. Now, fixing a parameter a greater than 1, we obtain the following inequality. Number of zeros in the ball of radius r is bounded asymptotically by log of mu of f on the ball of radius r, ar, and there are certain constants which depend on a and on f of 0. Going back to the example of f of z equal e to the z minus 1, we see that in that example, zeta grows linearly in R, and so does log of mu. So this seemingly fixes the problem which we had in a naive interpretation. And now, ideally, we would like to have an inequality of similar type in higher dimensions. In other words, we would like to have a bound on the number of zeros of a map from Cn to Cn in terms of the maximum modulus of f. However, this idea is also seen to fail by famous example of Cornalba and Shiffman from 1972. Let us fix a dimension n, which is at least 2. Then we may construct an entire map from Cn to Cn such that log of mu grows rather slow, in fact slower than any polynomial, while the number of zeros can grow arbitrarily fast. This showed a striking counterexample to the intuition which was had of generalizing transcendental Bézout problem to higher dimensions. And Griffiths, in fact, wrote that this is the first instance known to this author when the analog of a general result in algebraic geometry fails to hold in analytic geometry. Griffiths was a big proponent of the transcendental Bézout problem, and this program was highly influenced by his ideas. And I wish to add a remark that under an additional assumption on the Jacobian of f at the zeros of f, one may in fact prove a Bézout type bound as conjectured, and such bounds were obtained by Yi, Lee, and Taylor in a series of work in 1990s. Now I would like to give our approach to the transcendental Bézout problem, and the first important notion is the coarse count of zeros. Let us fix an entire map from Cn to Cn, and let us fix a positive parameter delta and also the radius r. Now we introduce coarse count of zeros, which roughly speaking ignores small oscillations as follows. Denote by zeta f r delta the number of connected components of the set f minus 1 of ball of radius delta intersected by ball of radius r, and we only count those connected components which contain zeros of f. So if you look on this picture, by red we denoted 0 and the inverse image of 0. On the other hand, this small circle here denotes the ball of radius delta, and the inverse image of this ball are these three regions here. So now we see that there are 5 zeros inside the ball of radius r, given by these 5 red points. And however, these 5 zeros are naturally grouped in 2 clusters. There is one cluster which contains 2 points and another cluster which contains 3 points. And these clusters are given exactly by connected components of the inverse image of the ball of radius delta. Thus, we count this whole cluster as a 1 point, 1, 0, and this whole other cluster as another 0. Here we have a connected component of this set. However, this connected component does not contain any zeros of f, and thus we do not count it. Now one may see that in this case, the actual count of zeros is 5. However, the coarse count of zeros is 2. This is motivated by topological data analysis, and we want to explain what is the actual relation to topological data analysis. In this regard, I will first like to reformulate zeta in the following way. First, we notice that the number of connected components of the zero set inside of the ball of radius R is equal to the dimension of the zeroth homology of the following set. Notice that f less or modulus of f less or equal than 0 is equivalent to f being equal to 0. Moreover, the number of connected components of the set inverse image of the small ball inside the ball of radius R is actually equal to the dimension of the zeroth homology of the set where f is less or equal than delta inside the ball of radius R. With these two interpretations, we may see that our count coarse count zeta f r delta is equal to the rank of the map induced by inclusion. So we may include the set where f is equal to 0 inside the ball of radius R to a set where f is less or equal than delta. This inclusion induces the map inside zeroth homology. We look at the image of this map, and then we take dimension. And this is exactly equal to our coarse count zeta. Now, behind the scenes, there is actually an algebraic structure. By denoting Vt, the homology of sub-level set where modulus of f is less or equal than t inside the ball of radius R, we get a family of vector spaces which depend on this parameter t. Moreover, we see that if S is less or equal than t, then the set f modulus of f less or equal than S inside the ball of radius R embeds in the set when S is replaced by t, and thus we have natural linear maps induced in homology. Moreover, due to the functoriality of homology, we know that if we have a map from R to S and from S to T, and we compose them, then we are in fact getting the map which we would get from R to T by inclusion. These properties can serve as axioms to define an abstract algebraic structure called a persistence module. A persistence module is central object in topological data analysis. There is a very rich theory developed giving the structure of such modules and their various stability properties. There is a metric theory of these modules, and they are used in a number of studies inside the topological data analysis, but also somewhat in pure mathematics as well. Now, in this interpretation, our coarse count of zeros is equal to the rank mapping V0 to V delta. And this is a special case of a rank invariant, which is given by the following formula. So given two real numbers S and T, we'll look at the rank of Vs to Vt. Rank invariant is a very important invariant in topological data analysis, which is extensively studied. Now I want to show what is happening with the coarse count in the Cornalba-Shiffman examples. Recall that these were the examples which were countering the prediction about the transcendental Bézout problem in higher dimensions. So in these examples, we have a situation as follows. Depicted by red are the zeros of the function. And in fact, they are all contained in intervals of the form 2 to the k times 0, 1. And this picture is in R2, which is inside of C2. So this whole picture is for the functions mapping C2 to C2. Now we see that as we tend to infinity, there are more and more zeros on these intervals. And in fact, by the definition of these examples, we may pack arbitrarily many zeros on each of these intervals. In this way, we create a number of zeros which increases arbitrarily fast. However, what is depicted by blue are sublevel sets where f is less or equal than delta in modulus. In other words, the inverse image of the ball of radius delta. Now what we see is that somehow, while there are a number of zeros on each of the intervals, they are all contained in a same connected component of the sublevel set. And thus, all of these zeros are counted as 1 0, all of these zeros are counted as another 0, all of these zeros are counted as only 1 0, and so on. What is happening with the function is the fact that it oscillates a lot on a very small scale on this interval, and these small oscillations create a large number of zeros. By ignoring these oscillations, we are able to count all these zeros as simply 1 0. Now, if fixing any parameter delta, starting from certain k0, in fact, all these intervals are contained in sublevel sets of delta, and we have a picture as shown here. Finally, here is the abstract result which we proved. So let us fix a greater than 1, and let us assume that our coarseness parameter delta is inside of this range. Now, the coarse count of zeros is bounded by certain constant, and then something which depends exactly on the maximum modulus of f on the ball of radius r. Notice, however, that there is a dependence of 1 over delta on the right-hand side, and this is indeed with agreement of the Cornalba-Shiffman examples, because if we would let delta tend to 0, we would retrieve the classical count of zeros. However, our right-hand side would tend to infinity. Now let us look at the following example. This is a generalization of our example from the beginning when we had f of z equal to e to the z minus 1. So f of z1 to zn is equal e to the z1 minus 1 all the way to e to the zn minus 1. And in this example, log mu grows as r, while the number of zeros grows as r to the n. In the Cornalba-Shiffman example, one may compute that the log of mu grows as log r squared, while the coarse count of zeros grows as log r. This is for fixed delta. Now, our result would state in the dimension 2 that zeta is bounded by log of mu to power 3, delta being fixed. And we see that actually asymptotically up to this power 3, this inequality is sharp. What that means is that on the log scale, if we would take an inequality for log mu, up to a constant, we get a sharp inequality. And lastly, I want to leave you with an open question, which is whether the power 2n minus 1 in our inequality here is actually sharp. We know by this example that the optimal power is somewhere in between n and 2n minus 1, but we don't actually know what the exact sharp power is. That is it, and thank you for listening.